Alright, hello. So I have some stuff I want to test and see if it works for evolving the neural network better. Also, I think I'm going to take this opportunity to redo, not necessarily redo, but I have this learning machine JavaScript library. So first of all, like, I guess to give a reference for this, one sec, let me just... Alright, so I made, a long time ago, made a C# neural network library. It's alright, but I've made so many improvements, I've never actually gone and made another, like, actual good working neural network library. So I've been saying for a while I'm gonna do that, and I'm not just gonna make it in C#. I'm gonna do it in a few languages: JavaScript, C#, C, maybe even something like PHP. But before that, like, so then myself, I've had my own little JavaScript library, or I've had a few different neural net libraries that I just use myself that I've made. The one I've had that's worked really well for JavaScript here is this fixed point one learning machine.js. Super small, just trains using a genetic algorithm, doesn't do any back propagation. It does train the output layer with derivatives though. I think this is like the model I would use to release another neural net library because I think it performs really well. But I wouldn't use fixed points because I don't think people want to deal with fixed points like I want to deal with them. I would do it with floating points again. So I think that's what we might do. And in the process, I also want to test some other genetic algorithm techniques. This random stepping works really well, but I feel like I can actually use the direction, like I can actually find the direction of the gradient, if that makes sense. And then once I get, see, this is the issue, is almost what back propagation does is it finds the, like, neural networks are like dealing with hundreds, thousands of dimensions, so it finds like the 1,000-dimensional vector direction of the gradient to go to what it thinks is the lowest point. But the issue is that direction to that smallest point might not be the smallest point in the whole thing. It's just the smallest point relative to where you started the network. That's called false minimum or local minimum. So like the way you get, so that this random stepping completely avoids that by just randomly sampling around, not in a general direction. Like it follows the position of the smallest points, but yeah, it's hard to explain. It's like probability sampling based off what the best point so far is. But one of the things I've been looking into are things like triangulation. I swear to God there's a way to like triangulate, since the loss function is mostly linear in a lot of cases. If like we know the point we're looking for is here, and we've got like if we get like 3 sample points, I totally think that we can measure the distances. Yeah. So I'm pretty sure what you do is you measure the distance between the 3 sample points, and then once you have the distance between that, you should be, I think you can interpolate and sort of extrapolate. I might do a little triangulation test right now, like on Shader Toy, I think, just to help this, because, man, it makes things so much easier for me when I just go and make little visual examples of stuff to make sure the core idea is working before I extend to something bigger. Alright. And you know, I just realized my cameras and stuff are in a weird order. Alright. And I wish I could make this bigger. I know I can make the font bigger. Alright, so we're gonna have our source point. This is gonna be white. I'm just gonna put it at 0 to begin. Honestly, this is kind of a stupid example to do for a shader, because you could totally do this in JavaScript or something, but I don't know why. You know what, I guess it makes sense. I find shaders such a quick way to just test little things. Like, you can get so much done in such a little amount of code in shaders. Alright, and I guess I'm going to use do the triangulation points too while I'm here. Alright, I think I might visualize the gradient of source. We'll see. I need to decide what kind of function source is going to be. I think I'm just going to do a linear attenuation of the signal. I guess I'm going to do something like this actually. Signal equals length. So then the signal will attenuate from the center. Alright. I gotta like comb my beard or something. It's I don't know how, but it got like tangled on itself while I slept. I guess that's me lying on it. Alright, so first of all, I'm just gonna visualize this signal gradient. Oh yeah, so U is the screen position. I'm going to convert that to world or local position with an aspect correct. Alright, so this should, visualize the gradient. So there's our source right there. That white center is what we're looking for. Now I'm going to visualize the these right here, our triangulation beacons or samples, I don't know what to call them. So now I'm just drawing the triangulation points as little circles. I think I'll make them blue. Oh, I'm not outputting C, of course. There we go. Okay, that's a bit too big. There we go, that's good. Alright, so that's our first triangulation point. Now let's draw the rest of them. I actually think there's a correct way to draw this, I'm not sure though. Whatever. Alright, so if my theory is correct, in two-dimensional space, we should be able to locate the exact position of this signal from these points, knowing this is linear. If one of these points though, if like these form a triangle, if the signal point here is no longer in the center of the triangle, I don't believe we can find it accurately. And then the other thing to realize about this, and why this might not apply that well to neural networks, is that once you get to higher dimensions, for example in 3 dimensions, this becomes a very thin sliced triangle of the 3D space, and you still won't be getting very, like, it won't give you, it won't give you a, like, it's a thin slice, so a point can't be in a completely thin thing. You need a volumetric thing like a cube, but that doesn't expand to higher dimensions well, because once you have like 1,000 dimensions, it's just too many sample points. So, yeah. So that's why my whole idea is to use like blue noise sampling mixed with this triangulation, and I think even at higher dimensions it should be able to like zone in on the point over time, kind of make a good mix of both. Anyways, let's just try this triangulation. So I guess red is gonna be our I'm gonna make red as the test. I don't know what to call it. Alright, anyways, so now we need to try and calculate our estimated point from our 3 sample points. So we're going to do our 3 samples here. Sample 0, sample 1. And then from that we need to estimate so there are multiple ways of doing this actually. I could linearly interpolate between these, which I think is the proper way, or I think it's bilinear or trilinear interpolation at this point. And then the other thing I could do is sort of like weighted sampling, where each of these has its own weight and it does like a normalized blend between. We'll see. I might just try that first, because that's easiest. So this signal vector is going to be that normalized. And then to get the estimated point, you do dot 0, or together with the weights. Alright, let's try this. Unknown value, normalize. might be too many parentheses here. Operation result is undefined for value passed in. Didn't I just pass in a vec3? Like, dimension mismatch. Oh, that's supposed to be a float, derp. So that's kind of close. Let's see how moving the triangulation point or signal changes. Yeah, so that becomes very wrong once it goes outside. Yeah, okay. Definitely do better than that. That's what I thought. So the weighted isn't correct. Okay. So now let me think about how I would do the bilinear. So I think or it might even be trilinear. I interpolate between these first two, I believe. The question is, how much do I... How much do I interpolate between them? I guess maybe the ratio between the two. Maybe S1 divided by the sum of both of them. I think that, yeah. That seems right. And then we do that again. Going from this point to the third point, T2. Based off the signal strength from difference from this. Alright, let's see how that works. That's also a bit off. Let's see how it works when it goes outside. Interesting. Yeah, so what I'm looking for is to extrapolate, not get stuck here. I might need to measure the difference between both points or something. I could also just try doing this first part. Try and get this working perfectly first, where it should be on one sort of axis. So it should hopefully go to here. Although I guess I can see why it can't really tell. Okay, I guess this isn't actually linear. This would be linear. So that might actually be more correct. That went a bit too far. Yeah, that probably did go way too far. Divided by... Oh, these need to be absolute values. Actually, never mind, these need to be positives. Alright, let's try the next part again, but with linear. That's pretty close. Yeah, I can't go past though. How would I make it go past the point? I guess measure the gradients between all the points and add them up. Somehow do all the gradients together, I guess? I don't know. I think so what I'm thinking is you pick the point with the least value and then its directions to the other 2 points are sampled and interpolated. But I think I can do that without just picking the smallest point. So I'm trying to think of this as the kind of like measure sampling normals from derivatives in a distance function. So you sample the difference on each axis, but with these points, they don't necessarily represent a single axis. They're just like random points. So I'm not sure how to combine them then. Oh, maybe I'll just try just doing the derivatives. That's not horrible. It's pretty close, but yeah, I feel like it's not the right way to do it. Yeah, and it still doesn't leave the triangle. You know what? Let's look this up. Triangulation is done by the sine or cosine formula, where the distances between objects, the angle between them. Using these laws, we can calculate the distances. Okay, great. I wonder if I'm actually gonna... I swear to God you can do this without calculating angles. But maybe you do. Distance A, distance B. I don't know what the fuck they're doing. Oh my god. This is probably not the most elegant set of equations. No. Maybe I can just do this again, interpolating. Like, just do what I did before, but interpolate again. I'm gonna try that. No, still not going out of bounds. Maybe I need to normalize the signal. No, that made it worse. Yeah. Damn, you search up triangulation on Google and you get a bunch of like how to triangulate polygons and stuff. I am surprised how little comes up for triangulation. The use of triangles to estimate distances. I don't think it actually is completely accurate. The use of both angles and distances is known as triangulation. Holy shit. Multilateration is a navigation surveillance technique. Oh my god. I'm blown away how bad Google is these days. Holy shit. I'm calling it now. I'm gonna switch to searching on Bing, and I'm actually gonna find better results. Oh my god. I swear to god, Bing is actually giving better search results now than Google. What is this? What is happening in 2020?
If the words slipped down my mouth and found their way in your ear, I wonder what you'd say while you were asleep. I'm wondering who's laying next to you in your dreams.
Midpoint method. Each of the two images has a corresponding projection line.
Take a shot or two or four, any kind of poison to forget. now.
Oh my god, I'm not adding it correctly. Let's try this again then.
Hanging on your wrist. A little piece of me is just so quick to forget. I cut mine off and burned, and now I'm back in your bed. I never liked it easy.
Huh, that's weird. Let me try that different way. No, that doesn't work. No, and that's just wrong. That's actually going too far. So this is working, I believe. You can see as the point gets close to that, locks in. Oh, actually, I don't think it's working completely properly. Let me try setting it exactly to T1. Yeah, T0. That is not working completely. No, yeah, this didn't work. So I'm gonna test this with one line first, get it working with one line, and then extend it to the triangle. So it should be able to hone in. You know what? Shit. This is just technically like drawing a line, isn't it? Or like finding the distance function to a line. I need to find the closest point on the line. Or am I doing it backwards?
Lenny, fuck me.
that goes too far. Yeah, so this goes negative. So let's think about this. T1 has a smaller value. So this is going to end up negative, putting it back there. Huh. How much do we choose to interpolate, though, based off that small value? That's the question. I guess just clamp this to 0 and 1. Alright, let's try moving this around. I can just also create something actually that moves this around. That actually be pretty easy, or way easier to debug. Yeah, so it's not working completely perfectly. It should start shifting over more there. It only shifts over part way. So this needs to be normalized, I believe. But I'm not sure what it needs to be normalized based on. I guess maybe we have to assume the distance between the points is also yeah, because it's linear, the distance between the points is actually the normalization value, I think. Maybe not. think I got it. It's going a bit too far. Yeah, it seemed to go too far there. Alright, anyways, we'll try mixing it together. I don't think this triangulation method is going to work that well. I think I'm going to go back to the regular probability sampling. Oh, there we go. That's actually more correct. Yeah, that is definitely more correct. Okay. Now, I need to somehow interpolate to this third point.
But now I'll rise above you.
It seems to stay closer to this end.
You can never say what I have lost. You can never guess where I've been down. I can never break something that ain't wrong. Baby, come and chase what I have in store. but now I'll rise above you.
So this should be the equivalent of the other one, except this way. Where this should actually be along right, like right there. It should be following the line here, similar to this one does to there. So something is wrong.
Perfect.
So right there, it's more than halfway from the one point to the other. It should definitely be interpolating more than that. For some reason it isn't though. That's so weird how it's not, I guess it doesn't have the completely correct interpolation value. Because it's like somewhat correct there at 0.5. But when it goes over here, it doesn't stretch all the way. interesting. So can't tell if that's too much or definitely think that's going too much. Oh, I'm doing divide. I'm doing multiply instead of divide, of course. There we go, that's perfect. Oh, of course. I wasn't supposed to normalize it there. Alright, there we go. Now I'm going to change it to do the actual interpolation. Alright, hope this works. Kind of. I want to try and get it going out of the triangles, though. Definitely does match up when it goes close to the point. But it doesn't really interpolate along the side. Could somehow get like the complete gradients from this. Extend past. I just want to make sure this actually can extend past. I believe it can. Oh, it actually didn't extend past there. It should. I'm also going to apply a curve to this so it's easier to see. Now we can see where the point is a lot more precisely. So when it goes up there, it actually should go past. Yeah, right there, it should go past 1. So I somehow need to get the gradient You know what? This is actually pretty much my goal so far, though. Achieved is to get this basic interpolation where it's mostly correct inside the triangle. That's the huge issue, though. is I don't think it's actually as accurate as it could be inside. Yeah, I guess that's the reality. I'm also thinking, what kind of test do I want to build in the neural network? I don't know if I want to do another simple, I don't know if I want to do like a text generation network or something like that.
Yeah.
Yeah, I still feel like there's a better way to do this. But I'm guessing there's so many different ways you could do triangulation like this. Yeah, I still think I need to measure the gradients. Do just like uncontained gradients doing that. I don't know. Anyways, I've been thinking about this, and I want this to work with non-linear things like sine and cosine, so this probably isn't going to be what I'm looking for. I think I'm going to start actually programming a little test now. I just don't know what kind of example I want to do. Hold on, I'm going to go get some water. I'm going to think about what kind of test do I want to do. I think I might even do like a sine wave. Maybe just try to approximate a sine wave with as least little number of neurons as possible. Ah man, I'm really tempted to make like a little game that the neural nets compete against each other in, but that can get really complicated. Anyways, I will be right back shortly. Yeah, I think training to do a sine wave is probably the best. So let me just get this set up. Oh man, how do I want to do this example? As a separate file or...
There's a war inside my head, and I'm drowning in regret. When the lights come down, got an empty crown. My body's missing pieces, can't pull it all together. My body's missing pieces, I wish I could remember. My body's missing pieces, can't pull it all together. My body's missing pieces, I wish I could remember. There's a war inside my head, and I'm drowning in
I think I'm just gonna
regret.
take this and completely repurpose it.
When the lights come down, got an empty crown.
be understood until the concept of chi is made clear. Put simply, chi is on a physical level. Chi is the raw energy that we are breathing in and
every time I'm in the check.
Alright, so this neural network genetics generate function is where the magic's going to happen. Right now this generates between integers, but I'm going to have it output, I think values between 0 and 1, or I gotta decide. I think I chose 16 as the max multiplier here. I might do 4 as the max multiplier. Like, a higher max multiplier you get, the more chaos and chance of not a number and issues you run into, but like if you choose too low, you can't do certain things. Or the network can't scale up values enough. So this is what I'm going to test with the sine wave. I'm going to, I think, create different versions of this function and test it in a little sine wave test. Hold on, I'll be right back. So I'm gonna do no actual training here. I'm just gonna do evolution, so all it's gonna do is actually test the genetic algorithm. Our goal is to get it as best as possible in as little samples, or iterations are our samples. So I've stored the indexes of the input and output states in this layers array, and I can't remember what indexes I put it in, but the code right here is what does it. I'm trying to figure it out. I wrote this code so long ago. Alright, should measure the neural networks for 1,000 generations, and then we can measure what the best one was. And then we're going to output the actual data. Alright, I'm honestly surprised that this actually worked the first time I ran it, because I just wrote code for like 40 minutes, and normally when I write code for a while and then just run it, it has errors and things. So I'm guessing there's errors, it just didn't throw errors. So that's not that good, but at the same time it's alright. It actually did train a single slope downward. So now I can mess around with the settings and actually find better ways of doing this. This is definitely a really good starting point. You know, I'm actually thinking the triangulation could work better than this. We will see. Try some different stuff. Alright, this is really interesting. This is not working well at all. And this is actually what I found before, is that this method works absolutely best with the fixed points that I have in this. That the fixed points and quantization means that you have to search way less space when you're doing this random sampling. Yeah, and I don't really know how to get around that with, like, my whole thing is I'm seeing this with floating points, and I'm like, oh, I could floor the floating points to quantize them, and then it's like, well, why don't I just use fixed points then? So, try messing with the mutation rate and things. Yeah, this is not working. Let me try just random sampling. See, it's weird. I almost would think that there's something broken in this, because, you know what, I'm going to test the neural network. It doesn't seem to be, like, I've never seen it curve up and down yet, which it should have. Alright, so one bias and one weight for each hidden neuron. So this should output 0.5 always. This is weird. This shouldn't be too long. Only 7. Did I count something wrong? Oh yeah, there's no output bias. Alright, here we go. Now it outputs constantly 0.5. So that seems to be working. Let me test everything else. So it is mostly working. The triangle wave here is working fine. It's going up and down. So yeah, it's just the way it's training, or the way I'm generating the numbers. So yeah, I think if I can normalize the output automatically, it would just make everything better. I'm gonna try doing that. First though, I'm gonna go look, see about getting lunch. Be right back in a few. Alright, let's try normalizing. Actually, I wonder if normalization should depend on the input and output here. I think maybe it should. Like, should I normalize the weights and biases, or should I normalize the input and output? I guess it's both basically the same thing. Anyways, I'm gonna get going for lunch. There is so much. Every time I do one of these neural network streams, I'm like, oh my god, I could just keep testing this stuff forever. There's so many different things you can try and experiment with. Anyways, thank you for watching. I hope you enjoyed this this rare programming stream. Man, I really want to do more of these programming streams, but they take a lot out of you. They require a bunch of setup. It's not like, it's nowhere close to as easy as game streaming, but my brain loves to think so. Anyways, I'll see you around. Hope you enjoyed the stream. Hope you have a good day. Bye-bye.